Alright guys, so we've done naming before. This is just to serve as a quick review of how do you name acids and bases. The acids and bases that you have encountered most commonly are probably binary acids like HCl. What's the name of HCl? Shout it out. Good. Hydrochloric acid. If you are taking notes, you have 3 more minutes to finish whatever notes you have because you're just going to have to do those by yourself later. We are going to be kind of reviewing them as we go too, so I think that will help. Give me another binary acid, Praneeth, another one that would be very similar in how we named this one.
HBr.
Where's it at? Okay, HBr. Name it. Hydrobromic, right, hydrobromic acid. This table up here, give me another one that's a similar template because it's a binary acid.
Hydrosulfuric acid.
Right, so the first one up here, right? So it's hydrosulfuric acid. One more, Jillian, McKinley, Kim, you guys over there. Similar to that style binary. Okay, so hydroiodic acid. And so first off, we're noticing that all the acids start with an H. If it's a binary acid, meaning one and another ion, not a polyatomic ion, a general non-metal, it has that hydrofluoric acid, always. We really can't mess those up, I don't think. Now, what we usually have a problem with is you always want to say hydro when you want us to talk about an acid, but these other ones are polyatomic ones, which are ternary acids, and they contain a polyatomic ion, which you should know the H or I ending of off the bat. But we haven't seen them in a while, so it's going to take us a couple minutes to kind of get back in the groove. So, I'll start with this one. ICClO3, that's chlorate. How does chlorate's ending change when you're in acidic form? Ick, right? Remember ick, I ate too much? That kind of silly thing that kind of helped you with remembering. So chlorate goes to chloric, and you still say acid. Okay? What's ClO2? That's, well, what is just ClO2 1 minus? What's that polyatomic called? That's chlorite, and ites go to us, or os, whenever you are changing the name for an acid form. So that's chlorus acid. Okay? What's this one? What's PO4 3 minus as a normal polyatomic ion? That's phosphate. Phosphate changes to phosphic, but it's actually phosphoric. It sounds weird when you just say phosphic. If you put that, I'd be fine. But phosphoric acid. Ooh, what's this guy? C2O4. We don't often see that one. It's a very rare polyatomic. If you're listening to you, that's fine. Any guessers? It doesn't have carbonate has CO3. You remember oxalate? Now you do. C2O4 2 minus is oxalate. What's oxalate in acid form? Oxalic acid. Good. Okay, so that's a good start on the acids there. Now the bases over here have hydroxides, right? So hydroxide is a key word that's going to indicate to you that it's basic. And then on top of that, that's going to give us an indication of the pH and a number of other things. So, sodium hydroxide, this acts ionically. What's sodium's charge? You should be looking at your periodic table. 1 plus, right? What's hydroxide's charge? Hydroxide is 1 minus as well, crisscross, because it acts ionically. What's the formula? NaOH. Boom, done. What is aluminum's charge? Say again? Is everybody seeing that it's in the third group? So it's 3 electrons away from being noble gas. You should be looking at your periodic table for that. So aluminum is a 3 plus charge. What's hydroxide's charge once again? 1 minus. Okay, so that 1 minus crisscrosses down. What's the formula? Al what? What do I need to do to keep my 3 appropriately in its place? Put OH in parentheses. You must put OH in parentheses. Do not just put OH3 because that means there's 3 H's, not 3 hydroxides. You need to indicate you have 3 hydroxides. So that's what the parentheses is for. All right, let's do the last one. You guys can do this in your head. Look at magnesium's charge. Look at hydroxides. Crisscross. Tell me the formula. Mg. Parentheses. Thank you. OH2. Okay. So acids start with an H+. The H+ is indicative of the acidic portion of the acid. Bases don't have an H+, they have an OH-. And so what we're going to see is how they interplay together, how do they neutralize each other, where they fall on the pH scale, what are their properties. So we're doing a quick review of those notes. EJ, come back up here with us. Thank you. And from there, we're going to also do a lot of application with the different conjugate acids and conjugate bases, some of those definitions that were hard to like apply probably by yourself. So, oh, a couple more questions here. This is to make sure I know where you are. So I need some verbal responses here, okay? What does the pH scale look like? It goes from what to what? 0 to 14. 14 is the what side? Basic side. It goes from A to B, okay? So 0 to 14, A to B, so that's acidic to basic, and in the middle is 7, that we call neutral, okay? Describe how the concentration, this might be a hard one, concentration of hydronium ion changes from left to right. Hydronium is what formula? You probably wrote this down. It is H3O+, so H3O1+ is hydronium. It is essentially the same thing as me saying hydrogen, because hydrogen ion can attach to a water molecule, so H2O and H+ come together to make H3, which is where that 3 comes from, and that H right here, this hydrogen ion, can carry its plus charge with it and also attach to the water. So basically, hydronium is a hydrogen ion attached to a water. And this together, we still call acidic because it still has that excess of the hydrogen ion for itself. So if you know that H+ is indicative of an acid, on the pH scale, where do you think you have a large amount of hydronium ion concentration? Which side of the pH scale? The left, right? So you're going to have a lot of hydronium. A lot of it, because that's acidic. But over here, the basic side, what would you guess the hydronium concentration would be? Really low. Okay, so low hydrogen ion, or hydronium is another way to say it, not hydrogen ion. It's like tomato in this case. Okay, so hydroxide is indicative of a base. So where would the largest concentration of hydroxide be? Basic or acidic? So I'm sorry, one more time. I said hydroxide, OH-, is indicative of a base. Where would I have a lot of hydroxide? Basic region, right? So hydroxide is very large, so lots of hydroxide on the basic region, and then little hydroxide on the acidic region, because you're not going to have, you can't have both, right? Because if it's both equal H+ and equal hydroxide, what would that be? That would be neutral, because it's like the acids and bases cancel each other out, be neutral. So one end is going to be showing you it's acidic based on its concentration. We'll talk about the pH formulas in a second. Strong. That word strong meant something really specific. Look to your notes. Tell me what strong means. Go for it, Kim. Right, so 100% ionization is one way to say that, or 100% dissociation is another way to say that. So on your notes, you guys wrote down, I'm going to scroll down real fast because I think I need some space here. You guys wrote down your 6 strong acids. And strong acids, they don't necessarily mean that they're going to burn your face off or your hands off and your fingers, you're just going to have to come back with nubs. Doesn't mean it's going to be destructive. It just means literally that it has the ability to ionize 100%. What were your 6 strong acids? Start with their binary ones. Shut them out. H, hydrochloric, HCl, okay. HI, so hydrobromic, hydroiodic. Those are your 3 binary strong acids. What are your ternary ones? Nitric acid, sulfuric acid, and perchloric, and that was the ClO4 one. Those are the 6 strong acids, and what I mean by strong is that they 100% will break into their ions. You guys probably remember just a couple days ago we were writing these ionizations, or these dissociations of salts. It's exactly the same thing, but we're taking the acid apart. So this goes into forming H+ and Cl-. This makes, you tell me, H+ and I-. This makes H+ and Br-. This makes H+ and nitrate, right? Don't break that happy family of nitrate up. It is a polyatomic ion. Keep it together. Next, H+ and sulfate, right? Now this one has 2 H pluses, right? You see that 2 there? Okay. This one? And ClO4, 1 minus. Okay, that's perchlorate. So this 100% ionized, 100%, this HCl will break into its H plus and Cl minus. That gives us something very important to recognize, because what you'll notice is on your pH formulas, when you got to the pH formula section, it said like, oh, pH is equal to negative log of H plus concentration. This bracket, and this was not evident in the notes, the bracket like that, that means molarity. You need to write that down, write that down. That means molarity, it means concentration. And we're familiar with molarity. What's molarity's units again? Moles per, right, moles per liter of solution. So if I say, all right, guys, I have a solution of hydrochloric acid and it's 2 molar. If I have a 2 molar concentrated solution of hydrochloric acid, whenever this hydrochloric acid takes its H plus and Cl minus and breaks it apart, that actually still means I have a 2 molar solution, but it's now of each of these individuals, because it's a 1 to 1 to 1 mole ratio. If I have 2 molar of this, when it ionizes, it makes exactly the same number of moles of itself in the same volume of itself, so the molarity doesn't change. So that again is 2 molar. And so I could say, oh, I got 2 molar chloride as well, but nobody cares about chloride. It's not important for pH in that case, just the H pluses. And so this is just an important thought, because if I give you a concentration of these acids, these concentrations also represent the concentration of the H pluses, which that's the only part that's really, truly important, because the H plus concentration is what we're plugging into the pH formula. So if I said I have a, let's just do an example. Did you guys have a calculator with log on it? McKinley will pass around the calculators. Raise your hand if you need one. Thanks, McKinley. If I say, what's the pH of 0.123 molar HCl, this is your example. So this you might want to write on a separate sheet of paper, unless you left enough space for your pH calculation examples within your booklet. We're gonna jump around and do a couple of pieces that make sense together, and then we'll pause and practice. Thanks, McKinley. So if I say, what's the pH of a 0.123 molar hydrochloric acid solution, what you would then do is go, okay, I know that this means I have a hydrogen ion. Hydrogen ion and hydronium are interchangeable again. And once again, I'll just maybe note that here. In your pH formulas, did you guys have hydronium or hydronium or H plus when you wrote your pH formulas down? Had hydronium. So I'll try to stick with both of them. I also will show you there are some pH formulas on your sheet back here. They say H plus, not hydronium, but they are interchangeable. Okay, so I should know now that this is my concentration of my H plus, aka hydronium, so I know that this is 0.123 molar. So this is the information that I have to plug into my pH formula. What is the one pH formula that has has H plus concentration in it and nothing else? pH equals, look at you have 6 formulas in front of you on your little booklet. pH equals negative log of bracket, okay, H3O plus or H plus, whichever way you want to say it, right? So if I know that this is the formula, I can just simply plug in my calculator negative log, and this goes into my formula, 0.123 molar, and you guys tell me what the pH is. Shout it out when you're there. Say again. 0.90. This, guys, is the pH. Now, we have seen the pH scale. Where does this fall on the pH scale? Really acidic, like really close to 0, right? Does that make sense for hydrochloric acid? Yes or no? Yeah, because it's a strong acid. It's got a low pH. It's in the acidic realm. Yes, we're good. So that should give you a confidence boost, because you should be able to say, my answer makes sense because I know how the pH scale works. Okay, so since we're doing pH calculations, I'm going to continue here. There is another pH. There's 6 pH formulas. And with those 6 pH formulas, you can get many, many variables. You can get pH. What else can you get? What other unit or variable could you get? pOH, which is basically the opposite of pH. It's just we don't have a pOH scale. What else can you get? So pH, pOH, OH minus concentration, right? Bracket means concentration, that's molarity. And you could also get H plus concentration if you didn't already have it. Now, we actually started off with that, right? You saw that our acid here started us off with our H plus concentration or hydronium concentration. So right then and there, we were like, let's go ahead and get the pH. So we've already gotten the pH, and we already had this. Nick, you have a question?
Oh, yeah. What is anti-log?
Anti-log is the same thing as doing in your calculator 10 carat negative pH or 10 carat negative pOH, whichever one you're doing. Okay, we'll do an example of that in a second. Okay, so if I want to calculate those 4 quantities, pH, pOH, H plus concentration, and hydroxide concentration, you should be able to with your formula. So right now we're just going to use them, and then we're going to start to like try to push this aside so we can do it ourselves. So we did the first one, pH is equal to negative log of this. Let's go ahead and solve for OH concentration. Knowing that we have already lots of things available to us. We have the pH here. We have the H plus concentration here. If I want to solve for this, which equation could solve for this, knowing what I know? Look at your equations and see what you know of. Darcy. Equals 1 times 10 to the negative 14th. Okay, so what you're doing is you're picking the appropriate formula based on the information given. You can only have one unknown in a formula because that's what you'd be solving for. So she said hydroxide concentration times hydronium concentration equals 1 times 10 to the negative 14th. We know this, right? So we know it up here. We're going to plug that in here. So I'm actually going to rearrange my formula just to solve for OH concentration. So I'm dividing by hydronium concentration on both sides. That cancels over here, leaving me only with the hydroxide over here, ion concentration we're looking for. And in my formula setup, I already know the denominator, I'm going to plug that in. So 1 times 10 to the negative 14th goes on top. What goes on the bottom? Hydrogen. What's hydrogen concentration? You should have written this down. Anybody? 0.123, right? So this is that right there. Remember, H plus or hydronium, they're interchangeable. You'll hear me do both. So that value right there goes down here, 0.123 molar. And you guys calculate. Make sure you put parentheses around here. This is not optional. You should be calculating with me. Go to the calculator. When you put parentheses around your numerator there, that should keep your 10 to the negative 14th at the top. When you divide by 0.123, anybody got an answer for me? Can you say it a little louder? Negative 14th molar. Okay. So 8.13 times 10 to the negative 14th molar. All right, guys, raise your hand or give me a thumbs up if that's a huge number. Not a huge number, right? Teeny, 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 tiny, like 0.00813. All right, so it's tiny, tiny number. That's a hydroxide concentration. Hydroxide, is that indicative of an acid or a base? Let's go one more time. An acid has what in the front of its formula? H. This is an OH. Who does this normally describe? Bases, right? So if I have a low concentration of something that's basic, does that make sense with my example here? Low concentration of hydroxide if I'm dealing with an acid. Does that make sense with that? Yeah, an acid shouldn't have very many hydroxides in their solution, just a teeny tiny bit. And that's right. This is an acid. I have a teeny, 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 tiny bit of hydroxide in my solution, so that should make sense as well. we have very low little hydroxide from an acidic solution. Okay, last step. Let's calculate pOH. We can do it in two different ways. What do you guys want to do? Yeah. Usually not, because many times these are in aqueous solutions, which is in water, and water has, it's amphoteric, which is a word that means it can act as an acid or base. Water naturally just really quickly ionizes with itself. It takes a little H plus, a little hydroxide, so it's always going to be there just in small amounts. Good question. We'll talk about the bases and acid definition shortly. All right, I want to find pOH. What formula would you guys like to use, knowing we have lots of things available to us? I'll start you off. pOH equals negative log of OH minus. And that's what we have right here, so plug it in. So pOH equals negative log of 8.13 times 10 to the negative 14. You guys let me know when you're there. 13 point. Okay. Now, we don't have a pOH scale, but what you should notice is that the pH, which is indicating to us that it's an acid, it's really, really low. The pOH should be on the opposite end of that, and so it is. It's like towards the 14 side, so that should make sense in terms of its opposite H plus, or pH. So, and then we can do a double check to make sure all of our calculations have been good so far. What equation has pH and pOH in it? Look at your sheet. What formula has pH and pOH in it? Equals 14. Let's plug our numbers in to make sure that works out. What was our pH? You should have written this down. 0.910. What was our pOH? Right here, right? 13.089. I hope that equals 14. Pretty dang close at least, right? Approximates 14. You guys can do that kind of in your head. That should make sense. Yes, ma'am? No, actually they don't. pH, pOH don't have any units. They're on a scale, which we identify as acidic or basic. But the only thing that does have units are the concentrations, and that's why I try to be pretty deliberate with putting molarity where it belongs. So where did I put molarity? Right here, because I'm talking about the hydroxide concentration, which does have a unit. And here, because the H plus concentration does have a unit as well with molarity. All right, so I want to hit you with the calculations first to make sure I get questions. Yes, ma'am. No, just say pH equals that. It wouldn't be wrong, but it's better relayed that way. Okay, it's almost like grammar, perfect grammar. Okay, so let's talk about the definitions now. There were 3 definitions of acids and bases. 3 different people kind of put their 2 cents in and said, I think we should describe acids and bases this way or this way. We'll talk about the properties in a couple minutes. So these were your guys, and here's how I remember them. So I've had to, find stupid ways to help myself remember them because, as a 10th grader, 11th grader, you have a lot going on. So the way I remember these are Arrhenius aqueous. Arrhenius aqueous. What's aqueous mean? In water. And Arrhenius' definition was very narrow-minded. He was like, I just want to know how they act in water. How does an acid act in water? It makes hydronium, okay? So Arrhenius aqueous is how I remember what Arrhenius' definition is in reference to. So he said, okay, when they go in water, this acid, this is a generic form of an acid, HX, because it's just H with whatever is bonded to it, this H and this water get together to make hydronium, and the X gets left out by itself. And we've seen that. We kind of drew that example from our strong, weak conversation. So bases, this is the general form of writing a base, Y, which is a metal in this case, OH being the hydroxide. It just breaks up and it makes hydroxide in water, in solution. So Arrhenius' definition is very easy. It's just what we kind of have referenced before in aqueous solution. But that's not the only way that acid and base behave. They can behave in other ways as well. And so Bronsted, it's actually Bronsted-Lowry, Bronsted, Lowry, two other guys were like, Arrhenius, you got a good start on it, but I think there's more to be said about acids and bases. So they wanted to make a more inclusive definition that wasn't just in aqueous solution. So they said, just period, what does an acid do and what does a base do? So H's are donated from an acid. Does an acid have an H plus in the front? Yeah, it's got it, it's going to give it away. And bases, do they have an H plus? No. So another way that you'll see H plus described, so we already said H plus was the same thing as saying what? What was it equivalent to? H3O plus, okay, so these are plus one charges, is a plus one charge. There's one more word that describes that H plus. Go ahead and find hydrogen on your periodic table. Everybody go to it and find it. Do you have reference tables in front of you or have your own? Point to it. Alright, so finding hydrogen, how many protons does hydrogen have? How many protons does it have? One, because it's the first element, that's its descriptor, its atomic number is its number of protons. If you know hydrogen, right, just H+, you don't have a charge on it. If I have one proton, which has a positive charge, what do I also have to have to negate that positive charge? What other subatomic? Well, hold on, not just yet, hold on. One, what would negate a positive charge? An electron, a negative charge, right? So you're saying this hydrogen ion, or hydrogen, has a proton and an electron, okay? That proton is just saying I'm its atomic number. The electron is just negating the charge. What's its mass? Look at its atomic mass. 1. Who's contributing to that 1 mass unit? The proton. Does it have any neutrons? No. If it had a neutron, it would be mass of 2. It would be a proton of 1 plus a neutron of 1. That would be 2. It doesn't have a neutron. So that's what a hydrogen atom looks like. It's just 1 proton or 1 electron in general. So if I have an H+, how do I get that plus charge? Say again? Lost the electron. I can't lose the proton because I can't have 0 protons because then I wouldn't be an element, right? That is its descriptor of its identity. So if you take away the electron, what's left? Just a proton. Literally, that's why we call a hydrogen ion a proton because it's nothing else. It's a bubble with a plus charge in the middle. So this word, acids are proton donors and bases are proton acceptors. It literally means a hydrogen ion or ion of hydrogen. But those are the 3 equivalent words that I just want to make sure you're familiar with, that they are the same. Got that? Thumbs up? Okay, so with that, you'll see the definition being referencing proton. It just means hydrogen ion. So how do I remember this? So I was probably not the best 10th grader in the world, but I remember this by saying, you know what, guys? Bronsted acids, they're bad acids. Yeah, you gotta watch it. Bad acids. Bronsted acids are donors. Bad acids. BAD. What does that mean? Bronsted acids are donors of what? H pluses or protons or hydrogens, however you want to say it, but H pluses or protons are probably what you're going to remember. So, I remember aqueous Arrhenius. I remember that's how it acts in water. I remember bad acids are describing how Bronsted acids are donors. And I just know if the Bronsted acid is the donor, the other one can't be the donor. It's got to be the acceptor. And then lastly, Lewis. Where have we heard Lewis before? No. Lewis dot structures. What were the dots on the dot structures? Where are those dots? They were valence electrons. Guess what, guys? Lewis is not describing how protons and H pluses are moving. It's describing how electron lone pairs are being donated or accepted. You won't see this nearly as much, like 2% of the time you'll see Lewis. But you should note that they are acids, in this case, acids are acceptors of the lone pairs of electrons, and bases are the lone pairs of electrons that are being shared. So they're the donors. So you should have those definitions, but if you're identifying a couple more pieces of how do you remember that, I hope that you're adding to your notes there. So in this example here, what's happening here? Whose definition is this describing? This one right here. It's like, here, have a proton. Thanks. That's Bronsted-Lowry, right? Because you're showing the proton exchange. What is this one representing? Say again? Arrhenius, right. And that's because it's in aqueous solution, right, water. And then this one, you're seeing an exchange of what? Lone pairs. Lone pairs are Lewis. All right, thumbs up. Can I move on? All right, so let's apply the definition of Bronsted-Lowry acids and bases. On your sheet of paper, you're going to see something with conjugates. I'll come right back here. I got to go to my conjugates. So your conjugate acids and bases are going to have to be labeled in the products. So on your paper, next to the crossword, you're going to see some notes right here with the Bronsted acids and bases. Right? So if you look right here where my hand is, it says chemistry lecture notes, acids and bases. We're going to do the questions right below that. We're identifying the acids, bases, conjugate acids, and conjugate bases. So on your notes, you should have written down information about conjugates. So I'm not going to go over details about that right now. We're going to apply them. So here, I blew up your notes, so kind of bear with me here. I want to do a couple examples with you so you can track the changes over time. So, what's the name of this guy, by the way? Oh gosh, you got this. Acetic acid. That's acetate. Acetate's acetic acid. Okay? So this is acetic acid. We got water. We're making hydronium and acetate. What did acetic acid do? Remember, you're thinking about Bronsted-Lowry acids, which were proton or H+ donors or acceptors. Would you say that from here to here, it donated an H+ or it accepted an H+? It donated, right? So you go from here and you look for the product that looks similar to itself and you go, what happened? All right, I'm a donor. If I'm a donor, am I an acid or a base? And how do you remember that? Those are bad acids, right? They have the B, they match BAD, so Bronsted acids are donors. Okay, so if you're the acid, I'll look at your conjugate acid notes or conjugate base notes, whichever, and you should see that acids make conjugate. Look at your notes right in front of you. Acids make conjugate bases, CB. Label that CB for conjugate base. You should be participating with me in class. Thank you. All right, so if this H, or this acid here, it's a donor, who did it donate it to? To water. Okay, you can see that donation process to water because overall, water went from H2O to H3O+. Well, you can definitely see that I got an additional H+. Well, what do we call that when it takes an extra H+? We say it's accepting an H+, right? So it's an acceptor. So acceptors are bases, according to Bronsted-Lowry. If I'm the base here, I make a conjugate acid. So the descriptors are acids and bases are going to be labeled on the reactant side. Conjugate acids and conjugate bases will be labeled on the product side. And the reason that it's called conjugate is because if I reverse this direction of the reaction, if I go this way instead, look at the interaction between acetate and hydronium. Who's the donor in the reverse direction? Hydronium, right? Hydronium's like, hey man, I got this extra H. You want it back? Boom, you get it back. So that means hydronium is acting as an acid. That's why we label it conjugate acid, because in the reverse direction it actually does. And this guy doesn't even have an H+ to give. It's that acetate's got it all combined. You can't take its H from the acetate itself. It doesn't have an H+ to give, so it has to accept. So if I'm the acceptor, I'm called the base. And that's because in the reverse direction they act that way. I see some confused looks. We're going to do some more examples with this. This is, I think, one of the more challenging parts of acids and bases. Everything else is calculation-based. Okay, so next one, HCl makes or becomes what in the products? It becomes Cl-. Okay, so what happened from here to here? It donated. Good. So if I'm the donor, I'm the acid. And acids make conjugate bases, so you can immediately label that Cb. Okay, and so if I look kind of forward, I can see that the sulfite here becomes HSO3, so that's bisulfite. How did it get there? How did it become that? It took on another H, so it is the acceptor, it's the base. And bases make conjugate acids. So let's do maybe another one to kind of keep this up here. Look at this one. I always start with the first one, I just track the changes. What is ammonia becoming as a product? NH4. So you just look for the thing that's similar to what it looks like. There's only a slight change. So from NH3 to NH4, what has happened? It accepted a proton, an H+, right? So if I am the acceptor, I am the base. And bases make conjugate acids. Okay, you can't have two bases interacting, right? So you have to have this guy's obviously the what? It has to be the acid. And then we can just kind of double check. Like, okay, it's got H. That's a good start. I can look at the change. Oh, yep, it lost its H. It donated its H. So this acid becomes the conjugate base. All right, take 2 minutes. Do the second half. You can finish before me. Work on the crossword for a moment. All right, check yourself up here. A, B, C, B, C, A. Thumbs up. So this is acting as the acid because it has the extra H, and over here it doesn't, so it had to have donated. This one's A, B, and then conjugate acid, conjugate base. Same, not quite same actually, same beginning. And then the third example, acid, base, conjugate acid, conjugate base. Thumbs up. Give me a 1 out of 10. How do you feel about identifying acids and bases, and then conjugate acids and conjugate bases? So if you're like 10, you're like, I am perfect in all ways. Okay, yeah, just give yourself a little slack. You don't want to be perfect, so that's a lot of stress. Okay, so I got some back and forth. Okay, so I'll work with some of you guys individually on that too. I have a couple more things I talked about, and then we're going to be working on pH calculations, and then also problem set 19A. Probably knock that out in class, I hope, anyway. So let me scooch back, so don't get dizzy. I'm going back to make sure I've talked about everything I need to for you guys today. So back to my original here. We did talk about strong being 100% dissociating, right? So what's the definition of weak? Just doesn't dissociate very well. And there's a way that we can describe that, and I'm going to give you like the generic acid. I'm not going to do a specific one, but HA plus water. And we draw a double-headed arrow, or two arrows back and forth. That means that forward arrow that we drew in the first place, that means 100% reacts. This is like, like a portion, 1%, 2%, 50%. There's not an actual percent because it's different for every single acid and base, but it's just not 100. And it's going to make some hydronium, just a little bit, and some, whatever this ion here is. So this reversible arrow means weak. So, your 6 strong acids, right? Every other acid in the world who's not those 6 strong acids are weak. Give me something that's weak. Anything that's weak. You got like, about 1 million examples you give me. You just can't say the 6 strong ones. I'll twiddle my thumbs until you're ready. Yeah. Hydrosulfuric acid. Good. That's not one of our 6 strong. Next. Hydrophosphoric acid. Okay. What else? Carbonic acid ain't strong, right? Keep going. And you guys drink that in your soda every day. Thank the Lord it's not strong. If not, your teeth will be gone. Say again? Hydrofluoric acid, though it does burn bodies in Breaking Bad, melts bodies, it's not considered a strong acid. It also eats through glass. That's what they etch glass with. You've seen like etched glasses.
Oh yeah.
That's what they use, and they have it at UNC Charlotte. They have like a one fume hood with all the hydrofluoric acid in it. It's like do not touch because it will like eat through your skin. But it's not considered strong because it doesn't make a 100% ionization. Give me one more. Say again. Phosphoric acid, H3PO4. So anything that's not on the list of 6 is considered weak. And weak means once again, what does it mean again? Doesn't dissociate 100%, but it's still in the acidic realm, right? It may be like at the 3, 4, 5 area if it's talking about pH, where strong acids might be at the 1, 2 range, but it's still considered an acid. So I think we got that. Definitions of these, this was on your reading guide. I don't think this was 100% in your notes, so let's just kind of think about what the prefixes mean, and then you tell me what you think they could mean. Monoprotic, diprotic, triprotic. Say again? 1, 2, 3, but what's the protic refer to? Robbie? Proton, and proton for us is basically the same as what? Say again? H ion, right? A hydrogen ion. So give me an acid that has 1 proton in it, 1 H plus in it. Any acid with 1 H. Hydrochloric acid. Give me any acid that's diprotic with 2 H's. Either hydrosulfuric or sulfuric acid. Something like this, it's got 2 H's in it. What's triprotic? Phosphoric acid or hydrophosphoric acid. Something like that. So just relate the protic to the H plus, and you're in good place. Those are the definitions. Thumbs up. Can I move on? Okay. So what were some of the interesting properties that you remember from the acids? They taste sour. And citric acid, lemon juice, anything like that that's citric acid. It tastes a little bit sour. What do bases taste like? Bitter. Who's ever said a naughty word and mom put soap in your mouth? Who's accidentally gotten shampoo in their mouth? It should taste a little bit bitter. Bases are bitter. Bases are bitter. You can remember the B and B there relationship. So in that reference, you should know the differences between those. And then I think that's all I want to do right now. Oh, bases are slippery. Soap is slippery. That's kind of common sense. And then, oh, I didn't go over strong bases. That's what I didn't do. Strong bases, and you guys wrote them down, and then in the notes, you probably didn't really understand what this meant, but I'm going to tell you now. It said mix a lowercase b with the shape of the periodic table. Your 8 strong bases, make a lowercase b with the periodic table. What's the first base? First metal ion? Lithium, and that's going to be lithium hydroxide. I'm just not writing OH right here. Next one? Sodium hydroxide. Next one? Potassium hydroxide. I might need some more space here. Oops, potassium hydroxide. What else? Rubidium hydroxide. Cesium hydroxide. Okay? And then now up the other side, up the group 2. Where's calcium next to potassium? Okay? Calcium hydroxide, strontium hydroxide, and barium hydroxide. They are all together on the periodic table. Doesn't that kind of look like a lowercase b if you kind of squint your eyes and turn your head to the side? Looks like a lowercase b. Bases form the B. Strong bases form the B on the periodic table. Does that make sense now? My little descriptor, what the heck does this mean, lady? Okay. And those bases again are strong. So lithium hydroxide, when it ionizes, it does the straightforward arrow, making Li1 plus and hydroxide. That's a 1 minus. So that's just an example of how that looks. Okay, we're going to do pH calculations now. We've already done one set, but I don't think that you're probably proficient yet. Looking at your sheet of paper, the ones where it says pH calculations lecture, I'm going to do a couple with you guys, and then if you guys are like, hey, we got it, you got to let me know, because I'm ready to set you free here. So pH calculations. So that you have the first one. So, is this the first example? Yes. So, number 1, the hydroxide concentration, or hydroxide ion concentration, is 6.4 times 10 to the negative 5th. you might want some paper, or I don't, unless you can organize your notes really well in here, there's not a lot of space to work with. I'm assuming you're right with your examples on. So you can see that most of the time I'm going to ask you to solve for the 4 quantities that would be related to pH. So pH, POH, H plus, or hydronium is your, whichever way you like to say it, and hydroxide. First off, what's already given to us? And number 1, we are given hydroxide ion concentration. Done. 6.4 times 10 to the negative 5th molar. You guys should have your pH formulas right in front of your face, okay? Because right now you've only seen them once, and I want to make sure you see them 5 times today. If I have hydroxide concentration, what equation can I plug into and get another answer? Say again? I can look at the formulas and go, the only one I can plug into and get another answer is POH, because everything else has like hydroxide, hydronium in it, pH in it. Like, I just don't have those values yet. You have to see which one you can plug into, and it's usually easy to tell because you can't have more than one unknown. So Darcy said POH is my next equation, and that should work for us, because POH is equal to negative log of OH concentration. I have that, right? What do I need to do? Plug it in, right? So I have hydroxide concentration already, and the next equation I can achieve is the POH one, because I only have hydroxide, so I can plug it into my POH equation. So in your calculator and on your paper, you're writing down your work for yourself, because you're going to want this to support yourself later. So negative log 6.4 times 10 to the negative 5th should give us like 4.2. So, and I think you should highlight or circle your answers really big and bold, because that's going to help you see what you have and know that you've answered all 4 of the quantities. So far, they gave us 1 data point of the 3. You used it for one other formula where you had 1 variable you knew and 1 thing you didn't know. Now, though, we have 2 quantities to work with. I can either use my hydroxide and get to hydronium. If I wanted to use my hydroxide and get to hydronium, what equation would I use? If I want to use my hydroxide and get to hydronium, which of these equations would I use? Yeah, Rishi?
Hydroxide times 1.
Say again? Okay, so you would use this one, right? So he said if I have hydroxide done, I don't have that, that's my question mark, and I have this, I can plug in there. Or if I have my POH, can I solve for something else too? Okay, I can use my pH and POH formula to get which equals 14 and find the other. I'm going to stick with the subtraction first, because I like subtraction. It's pretty easy. So I'm using this equation, and it doesn't matter which one you solve for next, as long as you get to all 4 in the end, you're good. So if I use pH plus POH equals 14, and I plug my POH 4.2 in there, I'm going to just subtract and say pH is equal to 14 minus POH, because that's how you rearrange your equation. Plug in my POH actually at this point in time. And what's 14 minus 4.2? 9.8. And that's equal to pH. Where? This? This?
One is a little mark next to it. pH plus POH equals
14.
Oh, that's 14.
Mm-hmm. You guys have your formulas, you can follow along. Okay, so at this point in time, you guys should realize, is this an acid or a base that we're dealing with? This is a base. Why? pH is above 7. This is basic. And at the end, we're going to reflect on that and make sure all of our quantities match what a base should represent. All right, we're still not done yet. And this is, I actually wanted to go this way because the only equation I've not shown you is that one that Nick asked about, which was the anti-log one. And so I want to make sure you know how it plugs in your calculator. So if I have pH, I can take pH and plug this directly into the equation that says anti-log, how's it written in your paper? Anti-log negative pH equals concentration of hydronium. This means 10 carat negative pH is equal to hydronium concentration. That's what it means to put in your calculator. So I'm going to put in my calculator 10 carat negative 9.8 because that's what my pH is. And tell me what you get. Carson?
Zoom into a button, or do I put the 10?
Put the 10 carat negative 9.8. I know, that's why I want you guys practicing your calculators, because sometimes your muscle memory will come into play and you're trying to work with your fingers there. Okay, so if you have a graphing calculator, you can use that, but I will say on your final exam you won't have a graphing calculator, you have to use the Evil Blue calculators.
What? Why?
That's the policy of North Carolina, so yeah, you guys can be frustrated, but there's not a ton of math, because it's cumulative, it's 40 questions with everything we've learned, so you'll be fine. Anybody got me? Darcy? 10 to the negative 10th molar, and this is my hydronium concentration. Okay, I have all 4 quantities. Let's go back and just double check that all of these make sense in reference to base. Is this a small number or a big number? 10 to the negative 10. Pretty dang small, right? Should I have a lot of hydroniums with a base? Yay or nay? Nay. And if you need to go back up here, we said acids have a lot of H3O pluses and a little hydroxide, bases have a low hydronium and a lot of hydroxide. Okay, so that makes sense. We shouldn't have a lot. Yeah, all right, it's pretty low for a base, so we're good here. Does this make sense for a base? Yeah, pH is pretty easy to understand in terms of it's on the 14 side of the scale. Does this make sense for a base? And you can do this as a comparison. Hydroxide 10 to the negative 5th versus hydronium at 10 to the negative 10th. Do I have more or less hydroxide? More hydroxide, because 10 to the negative 10th is a lower number, 10 to the negative 5th is a bigger number. I should have more hydroxide. That's a good thing. So hydroxide concentration is greater than hydronium concentration in a base. If that makes sense, because we're dealing with something basic. Okay, so take a breath. And I want you guys to proceed to the second example by yourself. You can work the person next to you, that's fine. But I want to see that you can get through 1 through 7 with me today. don't try to judge your numbers until you realize it's an acid base. You're going to have some interesting numbers. I'm here for you. I'm just walking around. The more you do with me, the less you have to do at home, so make sure you're proceeding. I'm just going slow, so that if you need to check your work, you're good. Yes.
If the question just asks you, it seems to ask you for pH, you still need to solve
Yeah, on all of these software report, it says at the very top. Yeah, the very top software report to make sure you're good. So you guys could pause for a moment and look back up here. Give me a thumbs up if you completed number 1. Thank you. So I'm sorry, my bad. Number 2. Number 2. Okay. So just a quick check to make sure you're making sense of it as you go. Nitric acid is an acid. Immediately you should be able to see that you have information for hydronium, because an acid delivers hydronium to solution. Plug it in your pH formula, you get a low pH. Yeah, that makes sense, because an acid should have a pretty low pH, and it happens to be a strong acid, right? Nitric acid, so it's going to be really low. And then opposite of pH is POH, and so it's a very high number, so that should make sense as you go, kind of making sense of the numbers, because sometimes you can get lost in the numbers. Then you see that your hydroxide is, oh my gosh, 10 to the negative 14th, high or low? Super low, and that should make sense. Hydroxide is basic. We have a strong acid here. We shouldn't have very many hydroxides, so that makes sense as well, and we're good to go. Keep proceeding through those. I'm coming around with extra help.
So we roll 8 together.
So I've had a couple of questions. Continue if you don't need me. But in a question, if it says I give you an acid and it gives you the acid, that concentration of that acid is automatically giving you hydronium's concentration off the bat that you're given initially. If they give you a base, if they say sodium hydroxide, lithium hydroxide, blah, 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 dinosaur hydroxide, whatever, if they give you hydroxide, it is giving you the hydroxide concentration. A base is giving hydroxide concentration off the bat. Raise your hand if you're number 5. Okay. I need to do number 5 with you because I need to make a quick change to that to show you a more deliberate example. So, yeah. Negative number? No, you're good. I'll just they're called super acids and super acids when they're really concentrated. So pause on your questions for a moment and in the middle of the question. So I hate to interrupt you in the middle, but finish that little last thing you're writing and then come back to me. So a couple of you guys are getting to the point where you're seeing some of the outliers of the examples. So if you come up with a negative pH or a number lower than 0 or a number greater than 14, normally most things lie in the 0 to 14 range. But if you are above 0 or below 0 or above 14, you're called a superacid or super base. And those are things that are really, really concentrated and they're very strong, so they make a lot of ions. And so that happens to drop the pH less than 0 or the pH greater than 14. Don't be scared if you get something above or below. It is accepted. It is an outlier. So that's one thing to denote. And also, I have number 5 up here, but I've changed the name of magnesium to calcium, so do note that for yourself, number 5. I'm doing that with you now because this is an example that we haven't done an example like this yet. So this is a calcium hydroxide. The only time that you'll ever do this are with the 3 dibasic bases. What are the 3 bases that have 2 hydroxides with them? 3 strong bases. I'll tell you one of them is calcium hydroxide. What's the other 2? Look, think about your lowercase b. Calcium. Who's right along with that? Is magnesium's not one of the strong. Strontium hydroxide. And another one just like this. Say again? Barium hydroxide. Okay, so these 3 bases, they do something special that the other bases don't do.
So for example, write this down for yourself. Calcium hydroxide has 2 hydroxides. And I'm telling you that your concentration of calcium hydroxide is 0.005 molar. When this ionizes or dissociates, it doesn't only make calcium, but it makes hydroxide, right? So that's CH2 plus, but how many hydroxides? 2. It makes double the concentration of hydroxide. You will never, ever, 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 ever do this with an acid. You will only do it with 3 bases, and these are the 3 of them that you do it with. So if I have a 0.005 molar calcium hydroxide, I have 2 times the amount of hydroxide. So what's my concentration of hydroxide? 0.0. Sorry, so 5 that goes up to 10, right? So it's going to be 0.010 molar. That is a point that there's no way you would have known that until I told you, so I need to make sure I do number 5 with you. So automatically you have a base. That base happens to be a special base that makes double the hydroxides because of this 2 right here. You're only going to do it these 3 bases ever. Calcium and 2 hydroxides. That means that my initial concentration, since I'm a 1 to 2 ratio, is doubled over here. So this is my hydroxide. That's my starting point. Hydroxide equals 0.010 molar. And from there, it's a piece of cake. You can do your hydronium and your pH and your POH because you've seen how to do that now. So just make a note of that. It's a special case. Continue. And that's why I didn't put the magnesium in there, but then I don't want to mislead them. They're not strong. They don't do that.
I'm making progress on it.
we have to solve for it? Sorry.
No, we use it to.
Yeah.
Alright guys, the rest of the time is yours. Work efficiently. You guys have about 10 minutes left. Do note that the homework questions are right below the lecture problems. They're on the board as well. And you have in front of you PS 19A. You see PS 19A on the other sheet of paper you got today. Look at it and take a look at it. And before you leave class today, I want you to make sure you ask me anything that you feel that you're not going to know how to do. But also, you're not going to have 100% of it done Monday. You're going to have about 75.
I have on that card somewhere. Because I was going to turn it in the other day, but you told me to skip That's fine, thanks.
Do you have, yeah, your working box? Do you have your notes from last night?
My notes from last night.
Were you in a booklet?
Oh,